Okay, good morning, everyone. My name is Daria Frank, and I'm a college lecturer in mathematics in Corpus Christi College. I'm also Director of Studies in Mathematics, so if you are going to apply to Corpus to read mathematics this coming year, I will be one of the people interviewing you. Now, I have been in Cambridge for about 10 years, and my research area is fluid mechanics with a particular focus on multiphase, turbulent, jets, and plumes. And that is what we are going to talk about today. Now, first of all, what is fluid mechanics? Fluid mechanics is the science of flows of liquids and gases. Formally speaking, if we divide mathematics into the pure and into the applied area, then fluid mechanics is most certainly a sub-area of the applied mathematics. However, that is not the entire story, because fluid mechanics is a very multidisciplinary subject, so it can also be regarded as a part of the physical or engineering sciences, and it is also influenced by biology and chemistry. This means that if we have a certain fluid mechanical problem, then it is often impossible to disentangle its different aspects, and we must consider it in its entirety and take into account all the contributions from the various disciplines here. Now, fluid mechanics is also a very vast research area, and it comprises itself several subdisciplines. Here, on the left-hand side of this slide, I listed some of these subdisciplines of fluid mechanics. So, for example, in aerodynamics, we study how the air flows around an object, for example, if we want to design a wing of an aircraft. Meteorology is a science of air flows in the atmosphere and also the science of weather prediction. In oceanography, we look at how the water circulates in oceans and how the sediments and nutrients are also transported in oceans. What else do we have here? So in convection and advection, we investigate how buoyancy-driven flows transport heat, mass, and contaminants. Then, for example, in biological flows, we look at how the blood flows in our bodies. Granular flows is a science of avalanches, or we look at how the sand dunes water in deserts. And also we can also consider reaction flows and combustion as a part of fluid mechanics. Now, the list here is by no means exhaustive, and it is also not mutually exclusive. So we can have a fluid mechanical problem that spans several of these subdisciplines, and also very similar problems can arise across different sub-areas here. Here on the right-hand side, I'm showing a couple of images that demonstrate a couple of flows that we can study as a part of fluid mechanics. So that is a snow avalanche propagating down the slope of a mountain. Here's a droplet bouncing off the water surface. That is a fire whirl which can form during a violent forest fire. And that image should be probably the most familiar to you, and it shows a wave breaking in an ocean. Now, fluid mechanics has been one of the major research areas in the Faculty of Mathematics in Cambridge for a very long time. In particular, we have a very large and dedicated fluid mechanics laboratory on site. This laboratory, which is called the Batchelor Laboratory, was founded back in the 1960s, and at that time, it was the first fluid mechanics laboratory associated with the mathematics department. Now, you may ask, why do we need a fluid mechanics laboratory as a part of the mathematics department? And the answer to this question is that the laboratory experiments are a very crucial component of the fluid mechanical research. By conducting a carefully designed experiment, we can gain insight into certain aspects of a fluid dynamical problem, and then we can use those insights in order to construct and develop theoretical models and also to validate numerical simulations. Now, today we are going to talk only about a very small part of fluid mechanics, namely about multiphase turbulent jets and plumes. So let me start just by giving you a very brief introduction into this topic. So generally speaking, a jet is a localized directed flow in the environment. And we call a jet a plume if it is arises or descends in the ambient due to its buoyancy. Furthermore, we speak of a multiphase turbulent jet or plume if it additionally contains some secondary fluid phases. So you can think of oil droplets and gas bubbles in water, or smoke particles and azotes in air. So here's a selection of images which shows a couple of examples of turbulent jets and plumes. So that is a smoke cloud rising after volcanic eruption. Here are some factory chimneys polluting our environment, and we can even produce a multiphase turbulent jet ourselves by using an aerosol spray in the bathroom. Now, turbulent jets and plumes have been a very vast and active research area in fluid mechanics ever since the fundamental work by Morton, Taylor, and Turner that was published back in 1956. The research program that I'm working on has so far been driven by specific problems on multiphase turbulent jets and plumes that are important and directly relevant for protecting our environment. Broadly speaking, we work in two directions. On the one hand, we study multiphase plumes and oil plumes in oceans. So we'll investigate how the contaminants are transported in oceans and what we can do in order to mitigate the pollution. On the other hand, we study multiphase turbulent jets and plumes on a smaller residential scale, and we look at how we can use those flows in order to improve our indoor air quality and also to reduce the energy consumption of our buildings. And as I have already mentioned, in our research, we conduct small-scale experiments in the laboratory, and then we use the results from these experiments in order to develop theoretical models and also to validate numerical simulations. Now, let us start looking at each of these two areas separately, and I'm going to start with the plumes in oceans. Now, many of you should probably still remember that image that was all over the headlines of the newspapers back in 2010. This image shows the fire at the Deepwater Horizon oil rig in the Gulf of Mexico. This fire occurred after an explosion took place at the Deepwater Horizon oil rig on the 20th of April 2010. And as a result of this explosion, a multiphase plume consisting of oil droplets and gas bubbles originated at the bottom of the ocean, and it persisted for over 3 months. Now, this oil plume was discharged into the environment under extreme conditions. First of all, it was released at very large depths, so at more than 1 mile depths. And then it also had a very large and varying source buoyancy fluxes. And these source buoyancy fluxes were larger than anything found in nature. So you can think of the source buoyancy flux of a plume as the amount of oil released at the source. Now, as the plume was rising towards the ocean surface, it was affected by several factors, such as the ocean stratification, ocean currents, and storms. And by ocean stratification, I mean that the density of water in the ocean doesn't remain constant, but in fact, it varies with the depth of the ocean or equivalently with the height above the plume source. Now, this oil plume was also released into a rotating environment, and because it persisted for over 3 months, it may well be that it was affected by the rotation of the Earth at some point. And now the main scientific question which now arises is, what was the resulting subsurface and surface distribution of the contaminants after this oil spill? And moreover, what we can do in order to mitigate the consequences of the oil spill. And in order to address these scientific questions, a consortium for advanced research on transport of hydrocarbons in the environment was founded. This consortium consists of several universities, many of them are the United States, and there are several groups of this consortium that study different parts of this very complex problem. Now, the main goal of this consortium is to try to understand and to predict the fate of the oil released into the environment, And that is important to know in order to minimize the risks to the environment and also to guide the response efforts. So, for example, there's a group that looks at the air and seawater interaction on the ocean surface and how this interaction affects the contaminants spreading on the water surface. Then another group is studying the chemical reactions within the plume, and in particular, how fast the oil biodegrades and how fast it sediments on the ocean floor. Yet another group of scientists is looking at how much oil is coming to the shore and what we can do in order to protect the coastal areas and the beaches. And today we are going to look only at a very small part of this very complex system, and we are going to investigate the buoyant plume dynamics close to the plume source. Now, I realize that many of you have probably never heard about the plume before this masterclass, and moreover, you have no idea what the plume theory involves. So I'm going to give you a very gentle introduction into this topic, and I'm going to try to avoid the mathematical notation as much as possible, and just to give you a very basic idea about what we can do with this plume theory. Now, when we talk about a plume, we usually mean that a fluid of a different density is released at some source. Now, usually that would be a point source, and as this fluid of different density rises towards the water surface, it is going to enchain fluid from the ambient. Now, the conventional enchainment assumption that we make is that this enchainment velocity across the boundaries of the rising plume will be proportional to the centerline velocity within the plume. And this enchainment constant is usually designated by some letter alpha. Now, if we make this enchainment assumption, we can write a system of differential equations that describes the dynamics of this rising plume. This system of differential equations will consist of three equations here. So B is here the half-width of the plume, and U is the typical centerline velocity of the plume. And this first equation here describes the conservation of volume inside the rising plume. This one is just the conservation of the momentum within the plume. And the last one is the conservation of the buoyancy within the plume. So the buoyancy, I mean the density difference between the fluid inside the rising plume and the fluid in the surrounding environment. Now, if we have a certain set of initial conditions at the plume source, then we can derive a unique solution to the system of differential equations. However, this solution will also depend on the conditions in the ambient fluid surrounding the plume. And we can have different cases here. The first one is when we are talking about a non-stratified environment. By non-stratified environment, I mean that the density of the ambient doesn't vary with height. For that particular case, we can derive that the main characteristics of the plume, namely the plume width, the velocity within the plume, and the reduced gravity within the plume, scale as these expressions here. I just would like to draw your attention to this expression on the left-hand side here, which basically tells us that the width of the plume scales linearly with the vertical height above the plume source, and it means that we are going to expect a typical conical shape in a non-stratified environment. Now, if we introduce a stratification into the system, that means if we let our ambient density vary with the height above the nozzle, then we will discover that the buoyancy flux within the plume is going to decrease with the height above the plume source. This means that if we start with a certain source buoyancy flux, then it is going to decrease continuously, and at some point it will reach zero. And when that happens, then the plume will stop to rise vertically, and instead will start to form a lateral intrusion. And using some dimensional considerations, we can easily derive that the height at which that happens is going to scale as some power of the stratification frequency of the ambient and also the source buoyancy flux of the plume. Now, if we additionally talk about a multiphase plume, that will get one more complication into the system. Namely, the oil droplets and gas bubbles possess the so-called slip velocity by means of which they can separate from the mean fluid flow and also escape the water plume. So in particular, if a plume forms a lateral intrusion, then the oil droplets and gas bubbles can escape out of this lateral intrusion due to this slip velocity. So now I think it would be the most instructive thing to do would be to see some videos of how the plume actually behaves. Here on the left-hand side, I'm showing you the video of a typical plume that is released into a non-stratified environment. So you can clearly see a conical shape of the plume, and then as the plume reaches the water surface, it starts to spread laterally. Now, what happens in the stratified environment? In the stratified environment, we can now see that the plume starts to rise. Then it starts to form a lateral intrusion at some height. Now, depending on the initial conditions, this lateral intrusion can be very close to the source. And now, because we are looking here at the bubble plume, you can see that the bubbles start to escape towards the water surface, form a vertical column, and as they travel towards the water surface, they will start to form several secondary intrusions and so on. Now, that is already a very rich and complex fluid dynamical problem, and we can study various features of this plume. So, for example, we can study at which height the plume is going to form the lateral intrusion, how many bubbles are going to be trapped within this lateral intrusion, and also what is, for example, the spacing between the secondary intrusions of this multiphase plume. Now, that would be the kind of typical questions that we would like to study in a fluid mechanical problem. So let's add one more layer of complexity and look at what happens in a rotating environment. So you may remember that at the very beginning, I told you that the Deepwater Horizon oil plume was released into a rotating environment. Now, conventionally, we characterize the effects of the background rotation on a fluid dynamical problem in terms of the so-called Rossby number. And the Rossby number is conventionally defined as the timescale of rotation to the timescale of motion. Now, because the oil spill lasts for 3 months and several rotation periods of the Earth, we conjecture that it might very well be possible that the oil plume was also affected by the rotation of the Earth. And that motivated us to have a look at the effects of the background rotation on the dynamics of a multiphase plume. So let me show you what happens. So when we conducted the experiments on plumes in rotating environment, we discovered a novel instability in the plume dynamics. So here you can see the experimental view from the top, and here on the right-hand side you can see the experimental view from the side. And now, as you can see here, in a rotating environment, the plume axis doesn't stay vertical. Instead, it is laterally deflected after approximately 1 rotation period. And once it is laterally deflected, it starts to precess into the anticyclonic direction. Now, this discovery of plume precession was quite a surprising phenomenon, and its most obvious consequence is that it completely changes the contaminant distribution within the water column compared to the non-rotating case. Now, here, these black dotted lines show you the typical shape of the plume that we would expect in a non-rotating environment. And you can see here that in the rotating environment, the lateral contaminants dispersion is considerably increased. And of course, this has very important consequences for our mitigation measures and for what we can do in order to stop the lateral spreading of the contaminants. Good. Now, let me show you a couple of other videos to demonstrate which kind of other problems we can study in a fluid mechanical problem. So that is a typical bubble plume released into a non-rotating environment. We have already seen this video. And here's what happens if we discharge this plume into a rapidly rotating environment. So now you can see here that the shape of the plume changes dramatically. We no longer have a conical plume structure. Instead, the plume boundaries are now almost vertical. There is a very erratic motion going close to the plume source. And also you can see here that the rising plume front disintegrates into the collection of vertical plume fingers and a collection of vertical edges. Now, that is a very dramatic change to what we can see in a non-rotating environment. So let me just play this video again. And that is a typical kind of problems that we would study as a part of fluid mechanical research. So we would try to understand what causes these changes to the plume shape, how the contaminants are then transported within this plume, and we will try to develop theoretical models in order to understand and to describe theoretically these structural changes within the plume. Okay, so let me just show you a couple of more videos here. So that is the plume in a stratified non-rotating environment. So we have already seen this video as well. And that is what happens in a rotating environment. So you can also see that the plume shape is also considerably changed in that case. Now we don't have any lateral intrusions anymore. Instead, the plume will start to form a wave which appears to be traveling towards the water surface and which appears to have a certain wavelength and a certain propagation speed. And that is also something that we would look for and try to understand in a fluid mechanical problem. One of the most obvious consequences that you can already see here is that this background rotation also considerably changes the contaminants distribution on the water surface. And that is demonstrated on this slide here. So that is, so now we are looking from the top towards the water surface. And that is what we can see in a slowly rotating environment. So the plume fluid first starts to spread laterally as it reaches the water surface, and then the boundary of the surface area starts to undergo a certain instability. But that situation is dramatically changed in a rapidly rotating environment. Now you can see here that the amount of contaminants reaching the water surface is dramatically decreased, and also the plume will start to undergo immediately an instability and form edges which can move very far away from the source, which means that we have a dramatic change in how the contaminants are transported on the water surface. Okay, so these are not all the surprises that we can see for plumes in a rotating environment, because in some special cases, the plume can randomly bifurcate and magically transform into a coherent vortex, which reminds us of the so-called tornado. That is shown in this video here. Now, at this moment, I think we have an understanding under which conditions this tornado formation is favored. However, we still don't have a good understanding about what exactly triggers this tornado formation. And that is a very active research area now. So we are trying to understand what triggers this tornado formation and moreover, what we can do in order to reliably control this tornado formation. And if we manage to understand this will also have some consequences about our understanding about how the tornadoes formed in the atmosphere. Okay, and just to summarize what we can study on plumes in a rotating environment, or plumes on multiphase plumes in oceans in generally. So we try to characterize the plume structure depending on different ambient and source conditions. with the ultimate goal to develop theoretical models about how the contaminants are transported in oceans. And one of the most central questions here is, for example, what is the fraction of contaminants that remains suspended within the water column, and what is the fraction of contaminants which reaches the water surface? And this question, of course, has very serious links to the coupling of chemical and biological models. So this means that the amount of contaminants remaining subsurface will be able to undergo some chemical and biological processes, and the amount of contaminants reaching the water surface can be then coupled to the large-scale circulation models in order to understand how the oil will move on the ocean surface and what is the amount of oil that will reach our coastal areas. Okay, I think at this point it is enough about plumes as contaminants sources, and let's switch gears a little bit and talk about multiphase plumes that can be used on purpose in order to control the contaminants transport in oceans and in order to reduce pollution in oceans. Now, let me just demonstrate to you here a very simple example. So if we have a ship lock between a salty seawater area and a freshwater area, then whenever a ship goes through this ship lock, there will be a horizontal current from the saltwater area into the freshwater area. And this intruding saltwater current can have very damaging consequences. So it can negatively affect the harbor areas and freshwater canals, because it can also contaminate agricultural and ecological zones and also pollute the drinking water reservoirs. And the question now is, what can we do in order to reduce this intruding current of salt water into the freshwater zone? And it turns out that there is a very elegant solution to this question. So what we can do is we can now place a bubble source at the channel bottom and then release bubbles. And these air bubbles will rise towards the water surface. And by doing so, they will form a multiphase plume, the so-called bubble curtain. And this bubble curtain will act as a virtual barrier between the saltwater area and the freshwater area. And of course, the question is this bubble curtain effective? And moreover, can we still try to describe the infiltration flux of salt water into the freshwater zone across this bubble curtain? And that motivated to conduct us a study that has recently been finished and published. So in this study, we basically conducted a very simple set of experiments. So we filled one side of the tank with salt water and the other side of the tank with fresh water. And then we released the bubbles at the bottom of this tank and looked at how this bubble curtain impacts the infiltration flux of salt water into the freshwater side of the tank. And by using the experimental results, we could develop a theoretical model to understand the infiltration flux across the bubble curtain from the saltwater side of the tank into the freshwater side of the tank. And these theoretical models yielded results that were in a very close agreement with our experimental measurements. And it turns out that if operated under optimal conditions, these bubble curtains can be in fact very effective, and they can prevent up to 80% of the saltwater intrusion from the saltwater side into the freshwater side compared to the unprotected case. Now, just to summarize what we are doing here is we can use the multiphase plumes in this example in order to control the contaminants transport in harbor areas. And also, what I'm not showing here, but what we can also do is we can use multiphase plumes in order to flush out polluted regions in oceans. Okay, and I think at this point, I'm just going to move to the second part of my presentation and talk a little bit about plumes on a smaller residential scale and how we can study multiphase plumes in order to improve the building ventilation and also to save energy of our buildings. Now, I think we all became acutely aware of the importance of a good building ventilation after the coronavirus pandemic started some 3 years ago. And you may remember that the first clusters of the coronavirus pandemic were mostly associated with very crowded and poorly ventilated indoor spaces, such as churches, cruise ships, restaurants, some food processing plants, and also prisons and schools. And very quickly we recognized that in order to reduce the airborne contaminant spread and in order to mitigate the disease transmission, we had to improve the ventilation of our buildings. However, it is easier said than done. And on the next couple of slides, I would like to show you some simple strategies that can be used in order to ventilate the buildings and also discuss the main challenges that we encounter when we try to understand how exactly the air flows within our buildings and the challenges that we encounter when we try to improve our building ventilation. So generally speaking, there are two main ventilation strategies. The first one is the so-called mixing ventilation. Here, the new air is introduced into the building, and the old air is extracted at pretty much the same location as the new air is introduced. And this leads to the so-called mixing ventilation, in which the interior of this building is well mixed, and the air has a homogeneous temperature and contaminants distribution. On the other hand, we can talk about the displacement ventilation. For this ventilation strategy, the new air is introduced at some location, and then the new air displaces the old air inside the building without really mixing with it, and the old air is extracted out of the building at some different location. And this is called the so-called displacement ventilation. Now, each of these strategies has its own advantages and disadvantages, and I'm not going to discuss this today, but I just would like to say that depending on the ventilation scenario that you would like to achieve, is the one or the other ventilation strategy might be more preferable than the other. And now, how can we actually ventilate our buildings? So we can either do that mechanically by using the air conditioning systems or some fans. And this mechanical ventilation usually leads to the mixing ventilation of the building. But then what we can also do is we can use the natural ventilation. So the natural ventilation relies on the temperature differences between the indoors and outdoors, and also on the wind blowing around the building. Now, some typical examples are shown here. So we can have a buoyancy-driven ventilation. So when the air inside the building is hotter than the outside air, now we are going to introduce the cold air into the system through a vent close to the bottom. Then this cold air is going to replace the hot air that will rise towards the ceiling. And this hot air is extracted through an upper vent close to the ceiling. Then we can also cross-ventilate our buildings. This means that we have one window on the one side of the building. The wind is going to blow into this opening, and then it is going to flush out the contaminated air out of the building that will leave the interior through the exit opening on the other side of the building. And then probably the most typical example that we can have here is the so-called single-sided ventilation. For the single-sided ventilation, we have just one single opening. It can lead either to the ventilation due to the temperature differences between inside and outside, or to the ventilation due to the wind blowing outside of the building. Now, these are just some very simple examples of a very simple model building with just one room. However, a real building is much more complex than that. So we have a complex geometry of the indoor space, so we can have multiple rooms and several floors. We can have connection doors between the different rooms. We can have multiple inlets and outlets of our ventilation system, and moreover, these inlets and outlets are not necessarily always known. And this will lead to a very complex airflows inside the building. So it is incredibly difficult to actually derive a theoretical prediction for the airflows inside the buildings. Furthermore, varying indoor and outdoor conditions, or for example, the varying outdoor temperature, means that a certain ventilation system might perform well under certain conditions, but might completely fail under different operating conditions. So you may remember the hot days during the last summer when some ventilation systems really struggled with keeping the indoor air temperature. And also inside our buildings, we can have several other factors, such as the heat sources, people moving around, computer equipment, and furniture. And all these factors mean that we almost have no chance of developing a good theoretical model for a certain building and predicting how the air will flow inside a certain building. So what we can try to do now is we can try to run some numerical simulations of the airflow patterns inside this building. But it turns out that this is also a very challenging task because the airflows inside the building are the high Reynolds number turbulent flows, which means that running numerical simulations inside these buildings is a very expensive task and it's a very time-consuming task. So summarizing what I told you here is that the prediction of the indoor flow patterns for a given building is an extremely challenging task. But what about people, you might ask? And in fact, people also introduce another layer of complexity into this problem. And in particular, people act as sources of contaminants and also as sources for multiphase plumes. How does it happen? That every time when we talk, cough, or just exhale the air, we produce a multiphase plume or multiphase jet. So our exhaled air is a mixture of heat, moisture, and also some droplets. And this histogram plot here shows a typical size distribution of droplets during a coughing event that I took from a previous studies. So you can see here that most of the droplets in our cough are in the microns range, and that is actually a very problematic scenario because we can distinguish between the nice droplets here that are larger than 10 micron size. So these droplets are quite heavy and they are going to fall to the ground very quickly and be removed from our occupied space very quickly. However, the smaller droplets are much more problematic. So these are the so-called aerosols, and these aerosols can remain suspended in the ambient air for a very long time and actually be transported and redistributed by the ventilation flows. And this means that they will contribute to the disease spread between different rooms and even between several floors. And this has been a very active research area over the past couple of years, namely trying to understand how these exhaled aerosol droplets combined with the ventilation flows and what we can do in order to improve the ventilation of our buildings and to remove the contaminants out of the occupied space. Now, this has all kinds of different challenges. For example, one of the challenges is that we as humans don't just act as a source of droplets, but we also modify the ventilation flows around us. How does this happen? Well, that sequence of images here shows some exhalation events during breathing and talking processes. Now you can first of all see that depending on our mode of speaking or breathing, the exhaled air will be directed into the different directions. So for example, even if we have here a mask on, we still see an exhaled air coming above and below the mask. But also what you can see here is that there is a hot air plume which rises above our heads. And this hot air plume above our heads will combine with this ventilation flow, with these exhalation flows, and will also modify the ventilation flows inside the building and inside the rooms. Now, the exact airborne contaminants distribution inside the room will be affected by what we do inside the room, how many people are in this room, and also how long they are going to stay in this room and what kind of activities they are going to perform inside this room. Now, there is also another way in which we humans can modify the contaminant spread inside the indoor environment. So let me just give you a very simple example of that. So let us imagine that we have a dirty area inside the corridor and a clean area inside the corridor. That would be, for example, a typical situation which we can encounter inside a hospital corridor. Now, when a person moves from the contaminated area into the clean area, what we are going to see is that there is a wake behind this person, and they are going to transport contaminants from the dirty area into the clean area inside their wake. And so the question is there anything that can be done in order to at least mitigate this transport of contaminants from the dirty air into the clean air? One mitigation strategy that we can think about is to use the so-called air curtain. Now, air curtains are the devices that have been used for a very long time inside the doors of the buildings in order to create the virtual barriers and to separate the warm indoor environment from the cold outdoor environment. So when you walk into a supermarket and feel the hot air coming from above, that is the so-called air curtain. So an air curtain is basically a plain turbulent jet, which is blown with a high velocity across a doorway opening. Now, what we can try to do is we can try to place such an air curtain across the pathway of this walking person and see what happens. And now this video is going to show you an experiment that we conducted. So that blue fluid here is a so-called air curtain. Now you can see a person going through this air curtain. And what you're seeing here is that the air curtain will cut a part of the wake and will keep some of the contaminants in the dirty area. So, and in order to give you some quantitative results here, so what we found on this side is that if we use such an air curtain, it can reduce up to half of the contaminants transport within the wake of a walking person compared to the unprotected case. So which means that we can use air curtains in order to try to mitigate the contaminant spread inside corridors. Okay, I think at this point I start to run out of time. So what I would like to do is just to give you a very short summary of what we talked about today. So we had a look at multiphase flows, and I hope I could show you that these multiphase flows can occur in many environmental, industrial, and residential settings. And it is important to understand the dynamics of these multiphase flows in order to control the contaminants transport in our environment and to create a clean and sustainable environment. And also, I hope I could show you that the multiphase turbulent jets and plumes is a very active and versatile research area, and there are still a lot of problems that we can try to solve here. Okay, I think at this point I stop talking, and thank you very much for your attention, and I'm happy to answer your questions.
Hi, Daria. Thank you very much for that. A couple of questions to start off with. Are there additional complications for plumes in the air, or do they work very similarly to plumes in water?
Yes, there are, because what we haven't talked about today are the currents in the ambient fluid. And so you can think about in oceans, there are also ocean currents, but if we go very deep towards the ocean bottom, these ocean currents will be very small. So the water will almost not move close to the bottom. That is dramatically changed in air, because in air we also have these winds, and so the air flows are much stronger than in water. And also air is compressible, so if we go towards the higher layers of the atmosphere, then we need to take into account the compressibility of air that we usually don't do in water.
I'm going to put a couple of questions together now, just to make sure that we answer as many. So a couple of people have asked about the mitigation strategies that you mentioned, so the air curtains and the bubble curtains. Have they been implemented? Do we use them?
Yes, the bubble curtains are used a lot in ship locks, mostly in the Netherlands. So because most of the ship locks in the world are located in the Netherlands, but the climate change is coming, so the sea water levels are expected to rise, so it may well be that we will need to use ship locks much more often now, and also the bubble curtains will be used in these ship locks as well. Regarding the air curtains, yes, absolutely. When you walk into your next supermarket, I don't know, Tesco, Sainsbury's, whatever you're using, you will usually feel this hot air coming from above, and that is an air curtain, yes.
A couple of people have asked, what is a ship lock?
Ship lock. So if you have a different level between, if you have a different level of water inside a canal, or a difference in the water level between a canal and an ocean, a sea, then you need to have like this engineering construction where a ship goes in, the water is filled or extracted, and then the ship can go out of this ship lock.
I would say for most people, they probably just know it as a lock. I think it's just the addition of the ship which makes people, I don't know, in German, is it a ship lock? I would be interested to know, actually.
No, I think it's called a ship. So most of the scientific literature is just think it as a ship lock.
Is it? Okay.
I don't know. You can have other locks.
But there is also, I think you're also talking about, I know this is true in the Netherlands, where they're trying to stop, as you put in your diagram, it's the intrusion of salt water into the freshwater system. So a lock also helps equalize different levels, but it's also to stop salt water intruding into a freshwater environment as well. So some people have asked, and have bubble curtains been used to contain oil spills?
Not, though it has been tried. At least there are some theoretical considerations how we can use to do that. I'm not aware of any practical example where that has been done successfully. Because for this Deepwater Horizon oil spill, so one of the complications was that it was released at the depths of more than 1 mile. So how do you get there?
Yeah. So someone asks, why did you get so interested in this? What sparked your interest?
Well, that is a very easy question. So when I was doing my master's degree, it was back in 2010. That is exactly when these two catastrophes happened, namely the Deepwater Horizon oil spill and the volcanic eruption on Iceland with this unpronounceable name of the volcano. And that is was very similar to what we were studying at that point. And that is what I thought, hey, that is something very interesting. That is what I would like to do.
So someone asks, could you just elaborate on the difference between a stratified and a non-stratified environment, and how does this actually affect the plume?
Oh yeah, the non-stratified environment is basically quite straightforward. So you have the same water density everywhere. Yeah, so it doesn't change with height, it doesn't change with depth, it doesn't change with the location inside your water body. Stratified environment means that the density of the water is a function of either height or the horizontal distance, or I don't know, it can also be, well, it is just a function of space. Yeah. So typically what we are talking about is that the stratified environment in oceans will be a function of the water depth. This means that you have a high water density close to the bottom of the ocean, and this water density is going to reduce as we go towards the water surface. Yeah, yeah.
Oh no, go on, Daria.
No, so I just wanted to say that the So this ambient density is going to affect how the entrainment walks into the plume and how the density inside the plume is going to change as the plume rises towards the water surface.
Okay, a couple of questions about the plumes in the second part of your talk. So I'm just going to again try and put a couple of questions together. So someone asked about how has research about plumes, have they affected our current knowledge of how disease is spread or how viruses spread? And has that been applied in the real world?
Yes and yes. So, as I mentioned, one of the very active research areas was to understand how we exhale the air and which mitigation strategies we can apply in order to reduce this disease transmission inside the indoor spaces. Yes. So, for example, specific examples, some buildings were retrofitted with a new ventilation system. Some guidelines were issued in order to keep our indoor spaces well ventilated and clean. But that is still a very active research area we're doing here.
Someone asks, so just going back to you talk about the rotation of the Earth affecting the plume. Someone asked, do we have to worry? Does the position of the moon affect the movement of oceanic plumes? I suppose, I guess, with the tides, possibly.
Yeah, I guess that would be the answer to that. So if we have the moon will affect the tides, and the tides will have also the effect on the dynamics of the plume. But because we are talking about very large depths, so that particular oil plume will probably not be affected by the tides, because we are talking about a very large depth at which this plume was released.
And actually, sorry, someone else actually asked, why does the rotation have such a massive impact on fluid flows?
Well, because we have an accelerated frame of reference. It's a physical term for that. I mean, if we are in a rotating environment, we are going to experience Coriolis force and centrifugal force, and these two forces are going to affect the dynamics of any motion, actually. Okay. I mean, that is something you should be learning in your A-level course on physics, I think.
So does the mathematics behind plumes, does that transfer to something like a nuclear explosion, or do you have to take into account too many other factors like heat and radiation?
Nuclear explosions is not a plume. Well, I mean, it's a slightly different kind of problems, but we can use the same concepts that we use for plumes also to understand these kinds of also problems. But if you're talking about like this cloud, which is going to rise after an explosion, that can also be described in terms of the Plume's theory.
Someone asked, why does the effectiveness decrease past a certain strength of the air curtain? The diagram showed a decrease in effectiveness past a point. Why is this so?
Yeah, that's a very good question, a very good observation, because the air curtain itself is introducing a mixing between the two sides of the doorway or the two sides of the corridor. So you can think about if we have an air curtain which is too strong, is going to increase the mixing, the self-induced mixing. So it is always a trade-off. So how strong can we make an air curtain such that it still cuts through the wake? And we shouldn't make it too strong, because otherwise it is going to increase the mixing itself by introducing this self-mixing.
Okay, so just trying to strike that balance, between, okay, interesting. Where else, Adita asked, where else might we see fluid mechanics playing a part in our day-to-day lives?
Have you had your cup of coffee or tea today? Have you eaten some honey for breakfast? That's all fluid mechanics.
So everywhere then, I guess.
Pretty much, yes.
So someone just asks, you showed in your diagram non-rotational environment. But someone's asked, but if Earth is always rotating, what examples are there of a non-rotational environment?
It always depends on the value of the Rossby number that I talked about. So if we have a motion which proceeds very fast, then we can basically neglect the rotation of the Earth. Now, a very common misconception is that if we drain, for example, our sink, then someone may have told you that this draining fluid will rotate in one direction in the northern hemisphere and into the other direction into the southern hemisphere. And that's just not true, because this motion proceeds over such a fast period of time that there is not enough time for the Earth's rotation to have any effect. Yeah, so you would have to drain your sink or your bath for longer than a day in order for the Earth's rotation to have any effect on that draining. So,
okay. A couple of other questions about stratification, which is, do non-stratified environments actually occur, or are they, or is it a simplification for an ease of modeling?
I mean, they do occur. So we have, I mean, if you just put in the water out of your water tap into a glass, this will be a non-stratified environment. Yeah, because the water will have the same density. As to how stratified or non-stratified the water is in lakes, canals, and oceans, so it will actually depend on the exact location or on the exact lake or water body.
Great. So talked about that. So a couple of questions. If people were interested in learning more about plumes and fluid mechanics, do you have any recommendations, books, or something else that they can access, Daria?
Yes, that is a very good question. So I would say come to Cambridge and study mathematics. And you can come to our laboratory and learn all kinds of fluid mechanical problems. I think there are kind of a YouTube blog by Tom Crawford, I remember, who is also looking at some mathematical problems. And there's also another YouTube blog that is a very good one. It's called FYFD. So the last two letters stand for fluid dynamics. The first two letters, FY, I let you figure out what they stand for. And I'm sure that I'm sure that if you write an email to James afterwards, he will be able to give you the link to this. Yeah, that is it.
It's in the chat. I just popped it in the chat for you. And someone asked, so we can we study fluid mechanics at Cambridge? So a couple of people actually answered that, I guess. Yes.
Yes.
Come be taught by you, right? Find out more about it.
Yes.
Okay, so I'm conscious of the time. We've got Ronan and Ed, so I'm just seeing if there's one sort of last question I can finish on. Well, you know what, Darren, what I would say is there are loads more questions, and I will, yeah, okay. If you could give one reason why you should come study maths at Cambridge, what would you give? Yeah, with one selling point, what would you say?
It's the most diverse course. I think one of the most diverse courses in the UK, and you can study all kinds of mathematics and all different mathematical directions.
Okay, so the variety.
Yeah.
Yeah.